Mastering unsupervised learning. Density-based anomaly detection algorithms work because outliers lurk in sparse territories. Why do density-based anomaly detection algorithms successfully identify outliers by clustering data points into regions of higher and lower density, enabling the detection of anomalies as those that lie farthest from these denser regions? Density-based anomaly detection algorithms are successful in identifying outliers by clustering data points into regions of higher and lower density, enabling the detection of anomalies as those that lie farthest from these denser regions, due to the underlying principles of density-based clustering and the characteristics of outliers in a dataset. The fundamental concept behind density-based anomaly detection is that normal data points tend to cluster together in dense regions, while outliers are scattered in sparse regions. This is because normal data points are often generated by the same underlying process or mechanism, resulting in a natural grouping or clustering of similar data points. On the other hand, outliers are typically generated by a different mechanism or other result of errors in the data collection process, causing them to deviate significantly from the normal data points. Density-based anomaly detection algorithms, such as TPScan, density-based spatial clustering of applications with noise, and its variants, exploit this difference in density between normal and anomalous data points to identify outliers. These algorithms work by dividing the data space into regions of high density, known as clusters, and regions of low density, known as noise or outliers. The clustering process in density-based anomaly detection involves two main steps: 1. Finding the dense regions, clusters, and 2. Identifying the noise points, outliers, that lie farthest from these dense regions. The first step is typically achieved by applying a density-based clustering algorithm, such as TPScan, which groups data points into clusters based on their density and proximity to each other. TPScan, in particular, uses two main parameters to control the clustering process: epsilon, and min-PTS. The epsilon parameter specifies the maximum distance between two data points to be considered part of the same cluster, whereas the min-PTS parameter specifies the minimum number of data points required to form a dense region or cluster. By adjusting these parameters, the algorithm can be tuned to detect anomalies of varying densities and sizes. Once the clusters have been identified, the second step involves identifying the noise points, outliers, that lie farthest from these dense regions. These noise points are typically scattered in sparse regions of the data space and have a lower density than the cluster points. The distance between a data point and its nearest cluster is used as a measure of its degree of anomaly or outlierness. Data points that are farthest from the clusters are considered anomalies, as they do not fit the underlying pattern of the normal data points. The success of density-based anomaly detection algorithms in identifying outliers can be attributed to several factors. 1. Robustness to noise. Density-based algorithms are robust to noisy data, as they can distinguish between true anomalies and noisy data points that may be scattered throughout the data space. 2. Flexibility. These algorithms can handle varying densities and sizes of anomalies, allowing them to detect outliers of different types and magnitudes. 3. Scalability. Density-based algorithms can be applied to large datasets, making them suitable for real-world applications where big data is common. 4. Interpretability. The clustering process provides insights into the underlying structure of the data, allowing for a better understanding of the anomalies and their relation to the normal data points. In summary, density-based anomaly detection algorithms successfully identify outliers by clustering data points into regions of higher and lower density. The underlying principles of density-based clustering, combined with the characteristics of outliers, enable the detection of anomalies as those that lie farthest from the denser regions. The robustness, flexibility, scalability, and interpretability of these algorithms make them a powerful tool for identifying outliers in various applications.